All right, good morning, everybody. I hope you're having a great day. Today, we've got a Codeforces round. This is Educational Round 101. I'll be competing in it and sharing my thought process, and then at the end of the contest, I'll share solutions to all the problems I know how to solve. I'm a little bit late, but we'll jump into it now and see how I can do. I also am on my other computer, so if things are a little bit off, that would be why. Looks like lots of solves as well. All right, problem A, regular bracket sequence. We know what a regular bracket sequence is. You're given a string or a sequence of n characters containing brackets, commas, periods, and or question marks. There's exactly one open and one closed character. You have to replace every question mark with either a close or open. Determine if it's possible to obtain a regular bracket sequence after. Oh, this is open, comma, close, comma, and or question mark. Got it. Okay. Yeah, I think we can go forward and then go backward, and if it's negative in either case, then we are impossible. Also, it has to be even length. Yeah, otherwise we should be fine. Okay, so for, well, array line would be this. C is closed, then C minus minus, else C plus plus, and then if C is less than 0, then sys out no, and continue outer. So continue outer continues to this outer for loop. Goes on to the next test case, and then we want to do the same thing down here, except we want to go in the backwards order. And then char c equals line at I, do the same thing. And we want to look for open. That'll decrease by 1. Otherwise, the answer will be yes. Oh, also, okay. So if line.length mod 2 is not equal to 0, then sys out no. Interesting. Yeah, in this one we should, oh, this should be counter, not C. All right, so we should be fine there. Submit this. Then on B, I guess we'll bring up CF notifications. Okay, got it. Red and blue. Monocarp has a sequence A consisting of n characters. Let's change our audio output so we can hear it. Yeah, we should be able to hear that, I think. Good. N characters, all right, or n plus m characters. He painted the elements in 2 colors, red and blue. N elements were red, the other m were blue. After painting the elements, he has written two sequences, R and B. The sequence R consisted of all of the red elements in the order they appeared, and B consisted of all of the blue elements. Unfortunately, the original sequence was lost, and Monocarp only has sequences R and B. Okay, he wants to maximize the value of 0, A1, A1 plus A2. Oh, that can be negative, okay. So you want the maximum prefix sum. Well, you're going to need some prefix of red, some prefix of blue, right? So it's the maximum prefix sum in one plus the maximum prefix sum in the other. This is going to be 8 plus 5 is the answer here, which is 13. Yep. It's going to be just 10 plus... Oh, yeah, I can beat that. Okay. Very easy. So, yeah, the idea here... Well, I'll explain the idea at the end. How about that? Then you can skip the end if you want to hear how to do it. This is, yeah, max1 is the max of max1 in C1. And then int M2 equals 0, and C2 equals 0 for int I and A2. Then C2 plus equals I, M2 equals math.max of M2 and C2. And then sysout M1 plus M2. Looks good. All right, unfortunately I'm very sick, so I'm gonna go blow my nose real hard.
Well done, sir. AC on problem B.
All right, awesome. Heard we got it, so it's good. On to problem C. Building a fence for our good neighbors. You want to build a fence that consists of n equal sections. All sections have width equal to 1 and height equal to k. You want to place all sections in a line side by side. Unfortunately, the ground beneath the fences is not flat. For simplicity, you can think of it as height hi. You want to follow several rules when following the fence. The consecutive sections should have a common side length of at least 1. The first and last sections should stand on the corresponding ground levels. The sections in between may be on the ground levels or higher, but may not be higher than k minus 1 from the ground level. Is it possible to build a fence that meets all rules? Okay, so I think I kind of understand. You want to build a fence where the first and last thing are on the ground, and then you want to like increase and decrease in the middle and stuff, but you have to stay within like some boundary of the finish. It's probably easier, since all these fences are the same height, to think about this as just a single point. So we pick a point here and then pick a point here, just like the bottom of the fence is the interesting part. And then yeah, then if we pick like the bottom can increase by up to k, or up to k minus 1. So we can move it up by up to k minus 1 or down by up to k minus 1. And we want to store what range it can be in. Yeah, so I think we can just do that. So we've got that for n, that for k. Derivative size n. Store like the minimum height we can be at and the maximum height we can be at. So then at the end, we want to print whether heights at whatever can be within that value. So turn heights at, okay, so if heights minus 1 is greater than or equal to min minus k minus 1, and heights at n minus 1 is greater than or equal to max plus k minus 1, then sys out yes, otherwise sys out no. Yeah, for each of these steps we need to see whether it's valid. Alright, so min minus equals k minus 1, max plus equals k minus 1. So we can move up or down. If heights, well, okay, so min equals math.max of min and heights at I, and then max equals math.min of the max and heights at I plus k minus 1. Now, if min is greater than max, there's nothing we can pick here, so continue outer. This is the outer loop. And I think we should be good there. Oh, also we have to print no. Voice crack. Sys out no. Yeah, so we should be fine. Let's see if this works. No, it doesn't, so why not? This test case is pretty simple. One test case. Yeah, okay. Min is 0, max is 0. Okay, so this is fine. So if this is, oh, we just want the min, right? Min equals heights at I, or n minus 1. Print yes. I don't know what that logic was doing before, but it was way too complicated. Okay, we're good. Submit code for that, I think. Are we going to have integer overflow? Probably not. We should be fine. Awesome. So we got it. We heard about the thing from CF notifications, so we're good there. Let's move on to problem D. Cell divisions. So you have some, man, I'm not doing too bad for how late I started. I don't know, maybe just good people don't do these contests anymore. Who knows? I don't know why not, though. Usually they're difficult enough. They're pretty good. You've got an array of n integers where ai equals I. So you've got like the identity permutation. Okay. In one step, you can choose two indices that are different and set one to the ceiling division of the division of the two, the ceiling of the division. Your goal is to make A consist of n minus 1 ones and 1 2 in no more than n plus 5 steps. You don't have to minimize this number. I see. Interesting. If you always divide the biggest thing by the second biggest thing, what happens? Then the biggest thing turns into a 1, right? So, yeah, for instance, let's say we had 1, 2, 3, 4, 5, right? If we pick the 4 and the 5, then after that we'll have 1, 2, 3. Oh wait, do we set the smaller thing? Yeah, then we make this a 1. If we make x equal to this 5, then y equal to the 4. Oh no, then it's a 2. Alright, so I see the issue with my logic. Because otherwise that would be way too easy of a problem. Yeah, but we can turn everything to 1 except for the 2, and then turn the biggest thing into 1 pretty easily, I think, right? So yeah, we can turn everything into 1 if we need to. But the issue is if we wind up with one thing that's too big, that'll take us like log steps, but we don't have that many steps. We need fewer. So we turn like a bunch of things into that. And divide by 1,000 twice. Is that it? All right, sorry. Yeah, so if we divide by 1,000, like every time we get to like its square root, we divide the biggest thing 2 times. So what happens there? So we've got 1,000, and then we turned it into, well, we have 10 to the 5th, right? 2 times 10 to the 5th. Then we have 1,000. Then we have 300. And we have square root of 300. $17. Okay, square root of 17. Oh, each step, do we just take the biggest thing? Or we take the biggest thing, decrease it to its square root? Yeah, the first thing above its square root. I think that's just the plan. I think that's legit, because I don't think you can ever do better. What if, is that possible? Can you ever get stuck in an impossible state? Yeah, you probably don't get stuck in an impossible state because you never touch the 2 until the end. Yeah. All right, static class pair implements comparable pair. So we'll have an int index and value, public pair int index and value. This dot index equals index. This dot value is value. Public compare to some pair O if the value is not equal to O dot value. Return integer dot compare the value to O dot value. Otherwise, return integer dot compare the index to the other thing's index. Now we have all of our pairs. So we want priority queue pair PQ. Sorry if my face is in the way. Okay, this should be backwards though. We want the values negative. Okay, then tree set pair ts new tree set. To guarantee the sum of n is small. Yeah, okay. The number of operations, okay. So we'll have 2 array lists. And then we'll print these at the end. So sys out first dot size or dot first dot size. And sys out first dot get I plus a space plus seconds dot get I. That'll print our answer. We're gonna need print writer, but we'll do that in the end because it might be a bit tricky. So now for int I equals 0 less than n plus plus. pairs at I equals new pair, index I value I plus 1, pq.add pairs at I, ts.add pairs at I. So now we have all of these things. Okay, so while do we actually want to do this? All right, so on second thought, we're only going to add stuff to the true set if it's not 1. So if I is not equal to 0, then add pairs at I. Okay, so now, while ts.size is greater than 1, we want the, we don't need the priority queue even, I think. Pair max would be ts.remove, or ts.last. Okay, ts.remove the max. Pair next will be, okay, so now the target will be, it's an int target, I guess, will be math.square root of max.value, but also math.seal of this. And then we need it as a long, so math.round this to a long, then cast it to an int. Okay. So if ts.higher, well, okay, so now pair to use will be ts dot higher of new pair, the value or the index will be -1 and the value will be target. Okay, if toUse is null, then toUse equals ts.lower of new pair -1 target. So this is what we want to use. So then max dot value equals max dot value plus toUse dot value -1 over toUse dot value. And then if max dot value is not equal to 1, then ts dot add max. And then first dot add the max and seconds dot add the toUse. So max dot index and then toUse dot index. These are both +1. Okay, I think that's fine. So let's see if it works. One move, we set the second thing to 3. Okay, let's say this out, setting value of max.value to this out max.value. Setting value of 2 to 1. Oh, because these are backwards. Yeah, okay. Interesting that this isn't the best. How many moves is this going to take? Quite a few, so this is wrong. Yeah, this is too slow. Because if we do one, that, yeah, it's way too many, way too many. All right, cool. So this is why we think before we start typing up our solution. Okay, so what would a better idea be? For everything that we don't want to use, yeah, okay, so not equal to 2. This out test, and then test equals math dot seal of math dot square root of the test. What is this? This is math dot round of this. There should be a better way of doing this in Java. Maybe I just don't know what it is. Okay. There's 5 moves. There you go. Okay. Good. So how many moves does this take? This takes 1, 2, 3, 4, 5. Yeah, okay. So that's it. All right, try number 2. Okay, so for int I equals n minus 1, I is greater than greater than 2, greater than 1, I minus minus. Yeah. So now if I times I is less than n, then we want to decrease n. I guess this is a while loop, right? Let's make it a while. Then decrease n. Less than or equal to n. So in this case, n equals n plus I minus 1 over I. That's how you do sealing with integers. Then what else do we have? Sys out I plus a space plus n. Or I guess n divided by I, so like this. Yep. Otherwise, sys out I plus a space plus n. We just need array list for these though. This is just on equals n, and this is index on. Yeah, okay, so this is fine. I think that's good. So now sys out a dot size for int I equals 0 is less than a dot size plus plus. So a dot get I plus space plus b dot get I. Then we need a print writer. To do this stuff. Close, thank you. I think we should be good. Oh, nope. Multi-test case got me again. 1, 2, 3, 4, 4, 2. Uh-oh, 2, 2. Okay, let's work through this on paper. 1, 2, 3, 4. 3, 4. So now this becomes a 1. 4, 2. So this becomes a 2. Oh, ON. Yeah, weird. Okay. This is a bit odd that it's like that. I guess this will
Problem D got wrong answer test 1, sir.
Wrong answer test 1. Really? Did we? Oh, huh, funny. Good one. Yep, because that doesn't work. Okay. Yeah, okay, I is greater than 2. So then while n is greater than 1, n equals n plus 1 over 2, a dot add 2, and b dot add the index of this thing. Yeah, I think that's fine. Okay. Good, 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 good. It's not good we got it wrong, but like, you know, could be worse. Okay. Yeah, there are surprisingly few problems. I guess D was a little tricky.
Problem D got wrong answer
again.
test 1, sir.
Why is that? Will you tell me? The only not 1 elements differ from 2. Test case 1. I think I literally print the same thing the judge says, don't I? Oh, I print them in the wrong order, maybe? Oh, this should be ON, and this should be N. Yeah. Three, 2, 3, 1, or this should be 2. Ah, what am I doing? Okay. Thank goodness I'm not penalized for that. That would be kind of disastrous in an ICPC contest. Burning 40 penalty points on filling samples because you didn't check it over. Okay. Let's go. Come on. Test case 3. I feel like it's right. Here's the real test, right? Just run the max case because it's so easy to type in 1,000. Whoa, why so long? What's here? Is that a TLE? That is a TLE. Why am I TLEing? This should be a long.
Problem D. Got time limit exceeded. Test 3, sir.
Okay, good. And this is why we test, ladies and gentlemen. It doesn't matter. I'm not too worried. We got plenty of time left. Okay. On to problem E. A bit similar. There's also problem F, which also has solves. Maybe let's check the scoreboard. Yeah, we're not doing well, but we already knew that. We don't need a scoreboard to tell us that. How are the good people doing? Yeah. So it looks like E is probably the way to go. Let's call two strings A and B, both of length K, a bit similar if they have the same character.
Well done, sir. AC on problem D.
Thank you. We knew that from a while ago, but all good. Two strings A and B a bit similar if they have the same character and some position. You're given a binary string S of length N and an integer K. Let's denote the string this as the substring starting at I ending at J. Let's call a binary string T of length K beautiful if it is a bit similar to all substrings of S having length exactly K. Find the lexicographically smallest substring of T that is beautiful, or report that no such substring exists. Okay, so we're given a string. We're looking at substrings of length 2. So if there isn't a run of all ones, then the answer is going to be all zeros. So a lot of times the answer is going to be all zeros. The question is, like in other cases, what if there's a run of all zeros and of all ones? I guess that's the case in this sample. Let's do some thinking here. They say 0, 1, 0. This, okay. So if you have all zeros, that doesn't work. If you have all ones, that also doesn't work. So interestingly, this works. Yeah, I guess just 0, 1 works always. So no, it doesn't work. It doesn't work for this position here. k can be arbitrarily big, right? Yeah. I see. So really, we're just looking for, right? The only time that a string doesn't work is if it has like exactly its inverse here. Yeah, that's when something doesn't work. So we can get all of the hashes of each string that don't work. Then we just want the lexicographically smallest one, the first one that doesn't work. Yeah. All right. I'll explain this at the end, but I know how to do it. So the idea is to use the Harmeyer hash, or whatever hash you like. But I'm going to use Harmeyer hash because it is a great way of doing hashing. I didn't invent string hashing, by the way. It's just my implementation, which I really like. I think it's quite clean and lets us do exactly what we need to here. And if you have the code, you just copy and paste it and you're set. Okay, good. So we have this. Now what do we need here? We need the problem statement. Where's the problem statement? Bit similar. Okay, good. Get me the statement. So it's nk and then the string. K equals this, k array line equals next to k array. So first we're going to get our prefix hashes. So now we have all of the prefix hashes, which means we can take substring hashes in linear time. So we need a hash set of Harmeyer hashes. And then we can go for int I equals 0, I plus k is less than or equal to n, I plus plus. Is that right? K is 1, yep, that's right. In this case, then we want set.add Harmeyer hash dot substring hash prefixes from I to I plus k exclusive. Good. Okay, and now we want to just check everything because there aren't that many things in the set. So char array res equals new char array k. Arrays dot fill res with zeros. Okay, so then while true, res at 0 plus plus if res at 0 equals 2. I guess we want some index, right? So int index equals 0. Res at index plus plus, res at index equals 2. If index plus, okay, so now index plus plus, if index is equal to n, then sys out no, and continue test case. So this will be the test case loop. So we'll go to the next test case. You just print no, right? Yeah. Okay. Otherwise, we keep going. So else break. So this is going to be another while true. then res at index equals 0. And move on to the next one. Okay, so now, but each thing in the line we need to invert. Alright, so we inverted each of those things, and I think we should be good then. So now, sys out, yes, sys out, yeah, okay. Well, give me a minute then, and we can fix this. So yes, and then print out res. Okay. So now build and check. Okay. Harmeyer hash. So this is really if it's k, and then cur.add character 0. Alright, so now we just need a replace method. Yeah, okay, so we just need a replace. So how do we want to do that? So void replace int index int char old, and then char new. I guess we'll call it now. So the power will be L minus index minus 1. And then v1 equals, or v1, yeah, equals v1 minus, well, first we need to pre-comp. Then we need v1 minus old times s1 pow at power mod plus, or mod 1 plus mod 1 mod 1. Same thing with v2. And then we need to add the new. This is a plus. This is now is what we called it. Yeah, I think that's fine. Okay, so it's not unreachable yet. If set.contains cur, if it doesn't contain this, then break. Otherwise, increment it. Okay. Then if you can't increment it, print null. Then replace. Okay, so we want cur.replace. The index will be the index. Old. Oh. Is the index actually index? Yeah, I guess it is, yeah. The old will be res at index. Now will be res at index equals 0. If it's a 0, replace it with a 1. Otherwise, replace it with a 0. I think that should be fine. Okay, that's very messy, but I think we can handle that. So now, if we run this, if we run problem E, nope, okay. Okay, so considering plus arrays to add to string, this. Considering 0, 1. There's an index plus plus. Yeah, if it's 2, then set it to 0, index plus plus. Okay, do this again. Oh, yeah. Yes, 1, 1. Interesting, we pass. Am I doing this wrong? Yeah, okay, so I might be incrementing this backwards. Let's see. So we want lexicographically smallest, right? Yeah, so I had them from left to right. And like the smaller things have the bigger power. So that's fine. It's just index should start at n-1 and decrease, or k-1. Index minus minus. If index equals -1, then print no. Okay. So yes 1 1, yes 0 0, yes 0 1 0, yes 1 1, bunch of zeros and a 1. Okay, good. Runtime, do we have any concerns? I think it's linear, I think. Just with a fairly big constant. That should be fine. Okay, then we need print writer. And out.close. Looking good. Submit. Can we AK? It's the goal, right? It's always the goal. Is time limit going to be an issue for that problem? What was the time limit? 2 seconds. That seems a bit tight. I don't know. 17. Okay, I'm not too worried. That was a cool problem, though. I did enjoy that problem. It's very, very interesting. Good use of hashing, I think. It's good. Yeah, I think we're fine. All right. On to the next one. We'll listen for CF notifications then. So last problem of the set. Power sockets. We decided to drop the legend about power sockets, but feel free to come up with your own. I like it. Define a chain. A chain of length 1 is a single vertex. A chain of length x is a chain of length x minus 1 with a new vertex connected to the end of it.
Problem E got runtime error test 54, sir.
Are you serious? For real? Oh, am I getting... Wait a minute. Oh, is this the issue? What? Is that really what's going on here? Okay, let's write a generator. Try to not make it big enough. One dot print line dot close. Okay. Throw your stuff and do this. Okay. This is kind of silly. To be honest, this is a little bit fine. Okay, good. Now I know how C++ people feel when they don't make their array big enough. That's going to take ages to judge, so we'll just sit here and wait. You're given n chains of length these things. You want to build the tree using some of them. Each vertex in the tree is either white or black. The tree initially only has a white root vertex. All chains consist of only white vertices.
Well done, sir. AC on problem E.
What was it? All chains consist only of white vertices. You can take one of the chains and connect any of its vertices to any white vertex of the tree with an edge. Wait, what? You can take one of the chains and connect any of its vertices to any white vertex on the tree with an edge. The chain becomes part of the tree, but both endpoints become black. Each chain can be used no more than once. Some chains are left unused. The distance between two vertices in the tree is the number of edges in the shortest path between them. If there are k white vertices in the resulting tree, then the value of the tree is the distance between the root and the kth closest white vertex. In other words, it's the distance from the root to the farthest white vertex. What's the minimum value of the tree it can obtain? So basically, the question is, what is the closest you can keep your white vertices? each of the lengths are at least 3. That's helpful. Because that means the middle of the chain will always be white. No, that's not true. But, like, yeah, it means the tree will get big fast. So it's going to be pretty shallow. Like, okay, that's not true. You might have some really long chains, but like if you build a tree of the chains, then that'll be shallow. Does greedy work? Wait, what's the question? Oh, you don't connect them how I thought you did. Gotcha. So you can connect like the middle of a chain here. What is the blue thing? And why is this not 5? What? Oh, so these things, like the colors are like first, second, and third ones that are placed. Okay, so here's the root. The kth closest white vertex. Oh. Yeah, okay. Got it. So the minimum value of the tree you can obtain. So in this case, you want 10 white vertices. Okay. To get 10 white vertices, you start with 4, right? What if I do this? Does my camera die? No, it doesn't. Okay. So then I can draw on the screen. I don't totally understand this yet. Like, I'm getting there, but come on, computer. You can open up Microsoft Whiteboard. Here we go. Come on, or just give me an old whiteboard. Just give me something to draw on here. So yeah, okay, so initially you have 1, and then after that, when you place your next chain, you lose that one and one other, so you have 4. And then after that, you lose 1 from the 4, 1 from the 7. So you have 9. Yeah, so the most you can get is 9. So if you add a chain of length 3, you lose 2, gain 3, so you gain 1. So every chain will give you 1 white vertex. I see. And it's like some sort of like reverse path decomp. Like you have to divide the thing up into paths. One, two, three, 4. In test case 3, oh, because we want it to the 5th closest vertex. 1, 2, 3, 4, 5, yeah. Yeah, okay. K can be wacky big. That's a problem. But it seems like, all right, is OBS dying here? Is OBS killing my computer? No, we're fine. Give me a new whiteboard. Thank you. Okay. Was that so hard? Okay, so we've got, yeah, so initially you just have this node. Then on the first turn, you're gonna have an edge like this, and then some tree over here. Going to be like this. Would you ever not connect it to the middle? No, you definitely always would. Yeah, you'd always connect it to this thing here. Because like there's no reason not to. Okay, then the next thing that you remove, you only care about the farthest one down. So next you're going to remove like this one, and then this one, and then this one, and then this one, then this one, then this one, then this one. And you probably also always want to place them in order from biggest to smallest. Yeah, okay, I think that's the case. Let's see. So what are we doing here? When we place something, so we've got the greedy, yeah, so the greedy seems to work. So we've got the greedy, but how do you do it fast? Like the speed is still important, so we need to do it fast still. So when you place this, you increase the number of white things in a continuous range of heights. So you've got like a range increment. I think this might be a seg tree problem. Range increment. You have like range decrement, which is the same thing. You just like set this from a 1 to a 0. In total, you only add a reasonable number of chains, right? In total, you only add n chains, so we don't have to worry about that. And the length only goes up to 2 times 10 to the 5th, so it's not that big. So we're fine there. So we need range increment. We need find minimum, like minimum non-zero. Range increment, minimum non-zero. Both of those you can do with the segment tree. Then we also want to know when is the first time the prefix sum hits x. Yeah, okay, so when does prefix sum hit x? And I think that's all we're looking for. How much time do we have left? 39 minutes. I think we can do that. Yeah, let's do it. All right, problem F. So let's start with the seg tree. So leftmost, rightmost. What do we need here? So int to prop, and then I guess we need a range sum, right? I guess let's make this a long to prop and then long range sum. Yeah. Public seg tree, or do we need anything else? I don't think so. In leftmost, rightmost. We also need a left child, right child. So if leftmost is not equal to rightmost, then int mid equals leftmost plus rightmost over 2. It's been a minute since I've written a seg tree. L child equals new seg tree from leftmost to mid. R child equals new seg tree from mid plus 1 to rightmost. Okay, then public void recalc. L child, or okay, what do I need? Range sum equals 0. Well equals L child dot range sum plus R child dot range sum. So now we need public long range sum, return range sum plus to prop times rightmost minus leftmost plus 1. Okay, public void prop. If leftmost equals rightmost, then range sum plus equals to prop, and to prop equals 0. Otherwise, and then we recalculate. Otherwise, L child dot to prop plus equals to prop, R child dot to prop, same thing. Set to prop equals 0 and recalculate. Okay, good. I think we have that. Public void range add int L R long dx. So if L is less than or equal to leftmost and R is greater than or equal to rightmost, that means it covers our range. So in that case, to prop plus equals dx, and then return. If L is greater than rightmost, or R is less than leftmost, that's case 2 or whatever, so we can quit. We just return, we don't care. Otherwise, we don't know. So L child dot range add LR dx, and then R child dot range add L R and dx as well. This only happens 2 times log n times, or like, yeah, per query, it only happens 2 times log n times in total. Okay, so we can do range add, we can do your propagation, blah, blah, blah. We need to propagate first. Good, okay, what else do we need in our segment tree? We need min non-zero. Okay, so let's get that. Public int min non-zero index. All right, so if leftmost is equal to rightmost, then hopefully we got it right. So I guess we'll just say if range sum. Well, first let's propagate. If range sum is equal to 0, then throw null. Okay, so now otherwise, if L child dot range sum is not equal to 0, then return L child dot min non-zero index. Otherwise, return R child dot min non-zero index. We needed one more thing, I think. We needed, when does prefix sum hit X? Okay. Public int, when does prefix sum hit X? Int X, okay. All right, so if leftmost equals rightmost, then better hit here. So if prefix sum, range sum, is less than X, then throw null. Oh, I guess just return -1. Might be easier. Okay. Otherwise, okay, so now we're not a kid, or we're not a leaf node, which means we have kids. If L child dot range sum is less than X, or is greater than or equal to X, then we care about, yeah, return L child dot when does prefix sum hit X. We should always propagate here, so we don't have to worry about it. And then otherwise, X minus equals R child, or L child dot range sum, and then return R child dot when does prefix sum hit X. So this is a long, returns an index, okay. All right, so I think that's our segment tree, so we should be good. So now what do we do here? Single test case, thank you. We're given number of chains and k. Int n equals this, long k equals this, array A, class S, start read array n, sort A, reverse A. Oh, ruffle sort, is that what I called it? Yeah, ruffle sort A. Let's reverse. Is there an erased out reverse? Really? No erased out reverse? That would be nice. Let's just add a reverse method here. Okay, now A equals reverse, what did I call this? Static int reverse. Oh, reverse A. Good, okay, so now we have this sorted in decreasing order. Int best, int best equals -1. So now for int I in A. So we need a seg tree. Use seg tree. So we'll have it go from 0 to 5 times 10 to the 5th. Should be big enough, okay. So initially st.update, st.range add. So this is LRDX. So from 0 to 0, we add 1 because we have one thing at that index. All right, so now we want the min index. So int mindex will be st.min non-zero index, st.range add from mindex to mindex add -1 because we're going to turn this thing black. All right, so now int ltail will be I over 2. And then int rtail will be I minus ltail minus 1. Okay, so now, and then the min height will be the mindex plus 1, or plus 2. That's where it starts. Yeah, because you've got the mindex, one below it is black, and then you have the next thing. So now st.range add from the min height to min height plus ltail minus 1, add 1. And then range add from the min height to the min height plus rtail minus 1, add 1. This is a really weird, ooh, it's light outside, look at that. Yeah, so we add to these things. How much time do I have left? 27 minutes, it's plenty of time.
Is that bothering you?
What? No, son.
Do you know anything?
I'm busy right now. Do I hate when you interrupt you totally lose your train of thought? What was I thinking about? Yeah, okay, so we add to this path. And then well, what do you do? I had this figured out. Okay, so we added the path. Oh, now we need to see if it's possible. So if st dot what is this? Well, I guess we can just do a check method. So check, oh, we also need k. Check for best the best, seg tree and k, and then best equals this. What's wrong with this method? Okay, so this is long. Okay. All right. So, if st dot range sum is less than k, then return best. Otherwise, long to, or I guess int first will be st dot when does the prefix sum hit k, and then once we have that, we say return math.min of best and first. I think that's the answer. Nope. Null pointer exception. Range add. Prop. It's in recalc. If leftmost goes rightmost, then continue or return. Okay, crashed again. Null pointer exception here. If range sum equals 0, throw null. Really? Okay, propagate. I'll try to do dot to prop, rchild dot to prop. And then when I say first min non-zero index, that's the only other thing I call, right? Yeah, so we just add an query. What's up here? Child dot range sum plus rchild dot range sum. Problem is range sum is not equal to 0. Range sum is equal to 0. Oh, after I range add, then I need to recalc. That is a problem, I guess. So we need to see how big does the sum get. How much time do I have? 20 minutes, sorry, one sec. Hi, can you turn that down, please? All right. What am I doing wrong? What am I doing wrong? So the sum is always too small. This is long. Okay. Oh. Yeah, duh. Okay, so we're actually fine there. Three, 4, and hopefully -1. Looks good. All right. $32 minutes to solve that. Not the end of the world. Yeah, it should probably be a little bit faster, but not too bad. All right, we got it. Nice job. Nice job to myself. Man, look, I'm like glowing. I've got like a outline around me like I'm an angel or something. I'm not actually an angel, but yeah, okay.
Well done, sir. AC on problem F.
Alright, so Monogon beat me. I did have a late start, but I can't blame everything on that, right? So let's say my late start was 7 minutes. So 7 times 6 would be 7 times 6, 42. Yeah, so I think he just won fair and square. Maybe I was a bit rusty. I also had some stupid wrong answers on D. But yeah. Oh well. Fun contest. I enjoyed it. Oh, Colin beat me too. Okay. I think, yeah, he's making a video for this too, so well, good job to him. Very close, very close. Anyway, yeah, so that's the contest. Let's go over solutions now, and then we should be good. All right, so solution time. We'll go easiest to hardest as usual, and starting with problem A. And then I'll show my code as well, as long as I don't forget. So for problem A, you want to make this regular bracket sequence. And regular bracket sequence is just like parentheses that work, right? You can have a closing parenthesis that doesn't have a matching open parenthesis before it. Hopefully you know what that is. Basically, yeah, like they explain it here, but like you want to match them up basically. Like the same way curly braces work, you want brackets to work like that. So you want to replace the question marks with either open or closed brackets so that you have the thing that you're looking for. We can do some example here. So if you've got like this, for instance, then you want to replace this with an open bracket and this with a closed bracket. And then these two brackets match and these two brackets match. So the idea behind this is as follows. There might be multiple solution ideas, but the first observation is each of these are always +1 or -1 towards the like total number of things you've seen before, right? The total number of open brackets. You have a bunch of +1s and -1s. You need the sum to be even, which means you need there to be an even number of things total. So if the thing is odd, it's just not going to work because you're going to have something in the middle that doesn't have a match. So yeah, so you have to check that first. If it is even, there are two ways that it'll be impossible. So it's the only way like one of these things is impossible is either if the sum doesn't equal 0, or if like there's some prefix that's negative or some suffix that's like it has to be negative, I guess. So in other words, if you see like too many close, like if you see something like this, if this is your prefix, then here we have one open but two closed. So if we go from left to right, we'll have one open here, then we'll have 0 open, and I will have -1 open, and that's like always impossible. So when we have this -1 open, that means this is where it is impossible. And if we have a question mark, well, the question mark we could use beneficially, right? So we could have an open, maybe a question mark, and then a close. We could use this as an open bracket if we needed to. So we'll count the question marks as +1 always, just like optimistically. And then we will just, like if we actually had to extract the answer, we'd make them whatever they needed to be. But we don't have to do that, so that makes it easier. So yeah, we'll do something like this. So when we have an open, we consider it a plus. When we have a question mark, we consider a plus, and then a close, we consider a minus. We want to see if our total ever gets negative, and if it does, that means it's definitely going to be impossible because we have too many closed brackets. Yeah, so that's the idea. So we do that once going forward and then once going backwards, but we reverse which ones count as positive when we go backwards. And that's the idea to how to solve it. The reason this works is because you need like some prefix that breaks you in order for it to be impossible. So that's what we are looking for basically when we do this. And then you can do arguments with flow and with Hall's marriage theorem as well to like kind of prove it. But basically, yeah, here's the code. This part is just mostly copied and pasted. You might be able to do it a little bit cleaner, but yeah. So if the length isn't 2, the answer is no. Otherwise, you go through each character. If it's a closed bracket, you decrease it when you go forward. Closed bracket means subtract 1. Otherwise, you increase it if it's a open bracket or a question mark. And then if it's ever negative, you print no. This is the same thing, except it just goes from right to left. So it goes from the length -1 all the way to 0. And if it's open bracket, in this case, since you're going right to left, an open bracket means like that's the harder part. So like that's the part that you don't want too many of. So you decrease your counter if you have an open bracket, or like a closed bracket if you look at everything backwards. And you want to see if your counter is over negative, same as before. So yeah, that's the solution to problem A. On to problem B, red and blue. So you have some sequence of integers, and you're going to paint them 2 colors. Yeah, you want to maximize the value of the biggest prefix sum when you interleave these 2 sequences. So let's do an example from one of the samples just to explain this. So in the first sample, we have 6, you've got 6, 5, 7, 3. One of those is -3. And then on the other side, you have 2, 3, -4. So let's draw these in blue, I guess, so they match. So what we have to do is pick like either the first element here or the first element here and write that in our answer, our final sum. 1, 2, 3, 4, 5, 6, 7. So let's say we pick the 6. So we pick the 6 here, and now maybe we pick the 2, and now maybe we pick the 3, now maybe we pick the -5, and now maybe we pick the 7, then we pick the -3, and then the -4. So if we look at like the 6, -5, 7, 3, they're in the same order as they were in this array. So that's what we have to maintain. So yeah, so we can do that. What we want to do is maximize the biggest prefix sum of this array. So the prefix sums here are going to be 6, and then 6 plus 2 is 8, 8 plus 3 is 11, 11 minus 5 is 6, plus 7 is 13, then 10, and then 6. So these are the prefix sums. The biggest one is this 13. What you can notice here, though, is when we look at this 13 right here, in fact, for any of these things, what we're looking at is going to be like, for this 13, the numbers we've used have been 6, -5, and 7. So we've used these numbers here. Then we've used the 2 and the 3, these numbers here. So basically, what we can do if we want to is we can use any prefix of the left side and then also any prefix of the right side and have those be all of the numbers that we've used in total. So that's what we can do, basically, and that's what we're going to do, which is basically all we're going to do is just like not even consider this array at all and just say, if we take the biggest prefix sum from the left and biggest prefix sum from the right, the sum of those two is going to be our answer. So here we have the prefix sums are 6, 1, 8, and 5. Those are the prefix sums. The biggest one is 8, so we take that. Here the prefix sums are 2, 5, 1. Biggest one is 5. So we take the 8 and the 5. That's where we get the 13 from. This is a mess of a screen, but hopefully that made sense. Okay. So yeah, that problem was actually quite easy, I thought. At least very easy to code. The code for it is this, so I use some variable names, which might make it a bit tricky. But n1 is the size of array 1, a1 is the first array, n2 is the size of the second array, a2 is the second array. And then this m1 is the max in array 1, and c1 is the like cumulative sum in array 1 is what it stands for. So yeah, so I just get the max cumulative sum in array 1, the max cumulative sum in array 2, and the answer is the total. You could clean this way up into probably just a couple lines if you needed to, but I just wanted to type it as fast as possible. So yeah, okay, that's problem B. Pretty easy as well. Problem C, building a fence. So in this problem, you've got some landscape, and you want to build a fence over the landscape, but you have some constraints, namely your fence posts are all the same height. They're all height k. And you need like 2 adjacent fence posts. They have to be above land, but they can't be too far above land that they leave a big gap like in the middle here. Like this part here, we don't want to leave a big gap. So like formally, I guess. Yeah, I thought this problem was pretty boring, to be honest, but whatever, we can do it here. So we're going to draw some fence posts. So like maybe we draw this one here. The next one we draw here. Then the next one we draw here. Goes up a little bit more. The next one we draw here. And then the next one we draw here. So this isn't allowed because these two fence posts don't cross. They can only like differ here. These bottom pieces can only differ by at most k-1. That's the farthest they can differ. And then also this gap that we leave here can be at most k-1. That's like the biggest that it's allowed to be. So instead of thinking about these as fence posts, let's instead think about them as just points. We're just picking the bottom of the fence post, and I think that's easier to think about. So we've got this point here, this point here, this point here, this one here, and then this one here. Any two of these can differ by at most k-1. And then we know each one has to be above this range and then below this range here, because we can't leave too big of a gap. So if we get rid of this whole picture, what we have is just a bunch of continuous ranges. So we have to pick some number in this range, then we have to pick some number in this range here, some number in this range here, some number in this range, and then some number in this range. And we know the numbers we pick that are adjacent can't differ by that much. They have to be pretty close to continuous. So maybe let's decrease this a little bit to make it more interesting. How about that? So we'll make these things a bit tighter. Okay, here's a better example. So now, when we have this, we can move the next fence post up or down by k-1. So we can imagine the range expanding like this. So this is k-1, and this is also k-1, this slope difference here. So now what we can do is we can start with, and the first, there's I guess one last constraint, which is the first fence post has to be located here, and the last one has to be located here. That's just like part of the problem. I don't know why, but that's what they said. So yeah, okay. So really this first one, we don't have this range. For the first one, the range is just this part here to this part here. So like it's just one value. But yeah, what we can do is like store what continuous range the bottom of the fence post can be at for right now. Then as we move right, we can expand it to be lower and higher. And then we can trim that range to only the parts that are still valid under all of the constraints that we're looking for. So yeah, hopefully that makes sense. So we would, like, initially we're looking at some range, maybe let's say we're looking at this range for this step. Then as we move over, we would expand it because the next fence post can be higher or lower. But then we want to trim it to be only stuff that's also valid in this range here. So we would get rid of all of this stuff. And now the bottom and top of what we can actually achieve are both of these. We can continue doing this for each position and get the value that we're looking for, right? Get whether we can do it or not. And we don't have to extract the answer, but we could if we really needed to. Okay, so yeah, that's the idea. Hopefully that made sense. I'll walk through the code. That might make it a bit more clear if you're not familiar with it. But basically, yeah, here's the idea. So initially, the max and min of what you're allowed to be is just, they're both going to be the height of the leftmost land because your fence is forced to be at that position. Then as you move over, your min can expand and your max can also expand. But your max or your min has to be at least the height of the land, and the max can't leave too big of a gap. So that's why I max the min with height of the land, min the max with the highest it's allowed to be. If this range is empty, that means the minimum is like higher than the max, right? So it's got to be above this and below this, which means there's nothing it can be. So in that case, I print no and continue. Otherwise, at the end, I just want to see, are we allowed to have this where it needs to be? Like, is the requirement in the problem, is that something that's legal in our range? And if it is, the answer is yes. Okay, that's problem C. That took longer than I would have liked it to explain. That's fine. Problem D I think should actually be pretty easy to explain because the solution's pretty clean. But basically, here's the first observation, which is if we go to my code, oh, okay, well, I guess I deleted it. So I won't put it up here on camera while you guys are all watching because I don't want to waste your time. But the idea is the number of times that you can square root something before it gets to 2 is like 5 or 6, right? It like takes like 5 different, you have to square root it like 5 times and then it gets to 2, which is coincidentally how many operations we have. So that's like what we're going to do basically. We're going to take some number, square root it 5 times, and that's going to be the extra 5 or 6 operations that we have. And then we're going to take n-1 operations where we set each thing to be 1 in one turn. So those are what all of the operations are. In particular, here is what it looks like. So let's do an example with like, let's do 12, for instance. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I know my face is in the way. Give me a minute. All right, cool. So we're going to use this biggest number as like a special, like we're going to use this to set things to 1, basically. So the first turn, we're going to say 11 divided by 12 ceilinged. That'll make this a 1. Then we make this 10 a 1. We make the 9 a 1. We make the 8 a 1. 7 a 1. 6 a 1. 5 into a 1. Okay, so now the 4 is interesting. So 4 is still bigger than the square root of 12. Square root of 12 is somewhere between 3 and 4, because 3 squared is 9, 4 squared is 16. So we set the 4 to 1. But now the thing is, with this 3, we want to set the 3 to a 1. But before we do that, we can actually decrease 12. That doesn't hurt us. Like, we can do that for free, because all of the numbers we have left are all, like, very small, right? So we can take care of the 12 using the 3, which might take fewer moves than if we tried to take care of it using just the 2. So that's what we're going to do. So if you divide the 12 by 3, then the 12 turns into a 4. So we turn this 12 into a 4 first. And the 4 is still bigger than everything else, or at least as big as everything else. So we don't have to worry about making it too small. But it like decreases the number of turns it takes to get this biggest number down to 1 from log base 2 of n to like the number of square roots that you have to do. And the number of square roots is faster because it's like 6 moves or 5 moves instead of 20 or like 17 or something. So that lets us do it in time. Okay, anyway, I'm kind of rambling here. So then, yeah, so we have this as a 4, then we turn the 3 into a 1. And now we're just left with this 2 and this 1 on the right. So we have to turn this number into a 1. So first we turn this into a 2, and then we turn it into a 1. We turn the 4 into a 2, then we turn this into a 1. So yeah, so here we've turned it from 12 to 4 to 2 to 1, which is faster than 12 to 6 to 3 to 2 to 1. We save a move there. So you can see how it would speed up. As it gets bigger, the number of moves you save gets like more significant. So yeah, that's the solution. Pretty simple. The code for it is also quite easy once you figure it out. Oops. The code for it is, these are my arrays of answers. I go from I equals n-1 to 3. I is going to be the number that I set to 1. As long as I can divide out I from the biggest number without actually hurting myself, then I do that. And then afterwards, I set this number to 1, as I explained. And then finally, I set the biggest number equal to 1 by dividing it by 2. But we know the biggest number here is going to be pretty small, right? It's going to be less than, well, it's going to be less than 9, right? So the biggest it can be is 8, since it's smaller than 3 squared. So this will take very few moves. Yeah, and that's the idea. Cool. So that's problem D. 2 more problems left. Okay, we're out of time here, but that's fine. Problem E and problem F. So for problem E, yeah, this one's kind of cool. basically, this is a really cool problem. I really enjoyed this problem. You have, okay, so you've got some string. Let's do their first example. They had 0, 1, 1, 0. So we want to find some other string that's a bit similar to every string, every like subsequence of length 2. It's really length k. In this case, k is 2. So it needs to be similar in at least one bit to this one, and to this one. So the answer in this case, there's only one answer, which is 0, 0. Or sorry, 1, 1 rather. So 1, 1, in this case, these two match. We only need one of the characters to match, so that's fine. In this case, these two match. And then in this case, these two match. So no matter how you slide this, there will always be at least one thing that matches. Another way to word this is you never miss every character. If you miss every character, then it doesn't match. So that's what we're trying to avoid. And the real question would be, what sort of things would miss every character, right? What isn't allowed? And basically, if we invert the string, then we have 1, 0, 0, 1. So the things that would miss every character would be 1, 0 would miss every character, 0, 1 would miss every character, and, or sorry, 0, 0 would, and 0, 1 would. So we're not allowed to have any of those three things. But we want the smallest binary string, the lexicographically smallest one, that doesn't match any of those things. That's what we're looking for. So there are probably several ways of doing this, but the way I chose was to use hashing. So we can get the substring hash of each of these substrings of length 2. And I just have code that I've written to do that. I wrote my own way of hashing things, and like I call it the Harmeyer hash. It's just like a polynomial hash, but it uses methods that I like. And yeah, so then you can get the hash of each of these things. You can throw all of those in some set, either a hash set or a tree set. And then once you have each of those, you can check every possible number starting at 0, like you started all zeros. And then you try replacing this 0 with a 1, and then replacing this with 1, 0, and then you just count up in binary. You'll find an answer pretty quickly, and you can change from one to another in amortized order 1 time using just like you can replace a character in the hash. So what does that look like? Okay, also, I guess I should cover, you're not going to hit that many things, right? You're only going to have to check a linear number of things before you find something you'll miss, because you've only added order n things to your hash set that are things you can't pick. So if you keep picking things, you can only hit order n different things before the thing that you pick is going to be something you haven't seen before. Okay. So in particular, I have this. This is my hash code. You can just stop and pause here if you need to. I'll just go through it. Yeah, I'm not going to explain how this all works because that would take a while. But the idea is there are a bunch of things you can do. You can add a character to the hash. You can replace some character with some other character. And you can you can append 2 hashes. I didn't actually use this, but you can do that. And you can also get the prefix hashes, so the hash of each prefix. This is just a convenience method. You can also get the substring hash. So if you have some substring, you want to get the hash of that substring in order 1 time, you can do that here. So what the actual solution does is first I get the prefix hashes of the line. Well, first I invert the line, right? So I'm looking at the things that you can't pick. And then I get the prefix hashes of those. I put all of the things of length k into a hash set. So now I can check if some string is illegal or not in order 1. And then I look through all of the substrings that I'm considering that are of length k. I want to see if there are any substrings of length k that aren't illegal. That's what I'm looking for. So initially I start with all zeros, and then repeatedly I'll replace the least significant digit with a 1, or I'll increment the least significant digit and then propagate that over as I need to in order to add 1 to the number. So I repeatedly add 1 to the number, and I just flip this bit, and then if it was a 1, I move over left 1, flip that bit, and I keep doing that until I run out of numbers. So in this case, if it was all 1s and then I tried to increment it, then I would set everything to 0, but then I want to increment a bit that doesn't exist, the bit at index -1. So then I print no and go on to the next test case. So yeah, that's the idea. As soon as I find something, then I just print it. And that's problem E. Okay, awesome. Last problem is problem F, power sockets. And this problem is actually like pretty simple. For a educational round problem, for the hardest problem in educational round, I thought it was easier than usual, but I guess that's fine. Let's see, how many solves did it have? 80. So I guess, yeah, it was probably where it should have been, to be honest. Maybe just a little bit easier than usual. But, yeah, so I figure that, like, if you're trying to solve this problem, it doesn't hurt to read it, so I won't, like, explain the problem too much. But the idea is, you've got, like the general idea is you start with one white node, and then you get to add these paths to it. So you like have some path like this. Maybe your path is 7 long, and you add the path like this. You always want to add it in the middle. You can do an exchange argument to show that this is always best. And then these two nodes become like black. You can't use these nodes anymore. So you can't connect anything to either of these nodes. Then you might want to add some other path. So maybe you had a path of length 3 to this node here. And now these two nodes become illegal. Can't use them anymore. So now the question is, if you build this tree in the best way possible, what is the smallest that the kth highest white node can be? What's the closest to the root that it can be? Now, if you're going to do that, there are a couple observations you want to make. The first one is that you always, like, the way you want to construct this tree is pretty simple. Every turn, you want to take the longest chain, because you want the longer chains to be higher up, because longer chains are more valuable. You have a limited number of spaces close to the root. So you want to take the longer chains and put them close to the root. You want to connect them to the root. You also want to connect everything in the middle of it. So yeah, that's the idea. You just keep doing that, and then you just store your best answer at each step. The thing to watch out for, though, is that these things can get very long, so you have to do this in a fast way. Yeah, that's the important part. So, okay, so what does this actually end up looking like? Well, what we're going to do is make some data structure that stores how many nodes, how many white nodes are there at each depth. So initially at depth 0, we just have the one white node, and that's it. But then when we add this, maybe we add something of size 5, then this length is at most like 10 to the 5th, but we don't change anything at depth 1, right? So depth 1 is still 0. 2, 3, and 4 all get modified. So these two, like we have one chain like this and one chain like this. So we add +1 here, +1 here, +1 here. Then we do another range add, +1 here, +1 here. We also need to subtract 1 from here because we've made this node now be black. We've changed it from white to black. So this turns into a 0 because we do a -1 here. So these are all just range updates. We can do those with a segment tree very easily. If you're not familiar with segment trees, there's a algorithms thread on segment trees. I think it's like episode 4. And that teaches you how you can do them. So if you watch that, you should be able to solve this problem. The next thing we need is we need to see where are we going to add it. Well, we want to add to the highest up white node. So we want to see what's the first thing in our segment tree that isn't 0. So what's the first 1 in our segment tree? And we can do that with the segment tree as well. And then finally, we want to say, when does the prefix of our segment tree hit k? When does it reach k? We can do that with the segment tree as well. So yeah, hopefully that made sense as an explanation. I'll go over how to do each of those things with a segment tree real quick. So yeah, okay, so in my segment tree, I store leftmost, rightmost, also the range sum and a lazy propagation value. Initially, the range sum is 0, lazy propagation value is also 0. So I have my recalculation methods, just recalculates the range sum. My range sum just includes the 2 propagation value because that hasn't been applied to the subtree yet. I have my lazy propagation, which just adds to the range sum if I'm a leaf, or if I'm not a leaf, I add to the propagation values of my 2 kids, and then recalculate for myself. And okay, range add, you've got these 2 cases. This is just normal segment tree range add. For the minimum non-zero index, you basically just go to your left kid if your left kid has a range sum that isn't 0. Otherwise, you go to your right kid. And to check when a prefix sum hits x, you can just say that if your left kid's range sum is bigger than x, then you go into your left kid, and it hits x somewhere in your left kid's child, so you can return right away. Otherwise, you subtract out whatever your left kid would have taken, and now the answer is going to be in your right kid, but you're looking for some smaller target. So yeah, that's what this is here. Okay, so those are all the segment tree methods. Very easy. The rest of this is just, you just do the greedy. So first you sort the array, then you reverse the array so that you go biggest to smallest. And then you find the minimum index. That's where you're going to attach this piece to. You turn that one node that you're going to add this to, you subtract 1 from it, and then you add to the 2 tails at the correct height. So that's this. Then finally, you check for your best answer. So to do this, you just see, is the sum of the segment tree big enough? And if it is, consider that as your current answer. Yeah, okay, cool. So that's the idea for the problem. And I don't know, it solved it. Unless someone manages to hack it, then I'm pretty sure that's right. So I think the idea is certainly right. It's possible that maybe there's some detail I missed somewhere, but I think it's probably right. The one thing that I think might be hackable, if you're gonna go try and hack my solutions, feel free to. The one thing that might be hackable is you might be able to find hash collisions for this problem if you look hard enough. I only used two mods, so it's they're probably going to be pretty tricky to find, but they also probably exist. So yeah, I'm definitely, you're going to pass any data, but if someone really, really dislikes you and really wants to break your stuff in hacking in an educational round, it's possible you could hack my e-solution by finding some hash collision and then getting a false positive there. Yeah, so I guess if you're gonna go and try and do that, good luck. Feel free to. You certainly have permission, but it's gonna be tricky and it's probably not worth it because yeah, in a real round it wouldn't happen. In a real contest it would definitely never happen. And you could solve it just by adding a third mod if I needed to. So all right, yeah, that's all for me. If you are in Division 2 and this was rated for you, I hope you enjoyed the contest and hope your rating went up. And yeah, that's all. Have a great day. Thanks. Bye.